This video is about non-standard impedances, coming from chapter 29, section 2 of the textbook. Now, we have had three different standard impedances so far. We have had resistors, which have the formula Z equals R. The impedance is just a constant, the resistance. We've had capacitors, Z equals 1 over J omega C. And we have had inductors, Z equals J omega L. So one real and two formulas for purely imaginary impedances. All three of these can be generalized to a single formula. And that is Z equals, and now we're going to put the J omega, and I'm going to multiply it by 1 second to make this number unitless, because omega is in radians per second, which is units just inverse seconds. So multiplying by 1 second makes this thing unitless. And now I can raise it to a power, say alpha, and I can multiply by a parameter, let's say m. This formula incorporates all three of these. For a resistor, I just need to get rid of this dependence on omega, so I set alpha equal to 0. And that just gives me Z equals M, which is the same thing as saying M is just the resistance. For capacitance, I can set alpha to -1. And now I get 1 second inverted times M is 1 over C. So M over 1 second equals 1 over C. Or M equals 1 second divided by C. And for the last one, alpha equals +1 to get an inductor. And I have 1 second times M equals L, or M equals L divided by 1 second. You notice that the units here, in all cases, M is just in ohms. So this is time constant divided by capacitance, or impedance divided by time. So all three of these come out being just M is in ohms, which is indeed what we want, because this first term here is unitless. Z is in ohms, M had better be in ohms. Okay, so why do we want to do this more complicated formula? And why doesn't everybody do it? Why is it non-standard? Well, the reason for doing this is that it gives us a way of modeling things that we can't easily model with standard impedances. Because if we take a look, what happens if we, say, put a resistor and a capacitor, or a resistor and inductor in series? Well, let's do a resistor and inductor in series. At zero frequency, we're just out here on the real axis at R. And then as frequency increases, the J omega L term becomes non-zero, and we will go up that way. And so this is R plus J omega L. And we can get to any point on the complex plane, but as we vary frequency, we're only going to be varying the position parallel to the imaginary axis. The real part doesn't change. Similarly, if we do a resistor and capacitor in series, we're going to start down at -infinity, and as the frequency increases, we will move up towards that resistor. So that's R plus 1 over J omega C. Notice the 1 over J is a negative J, so that gives us a position down here on the negative imaginary part. Unfortunately, not all real devices behave this way. In particular, we have some that behave more like moving up at an angle, so that starting near zero, moving up not parallel to the imaginary axis, but at an angle here. And we can get that with this more general formula if we have alpha between 0 and 1. 0 would be not changing, and 1 would be moving vertically. Similarly, we can have something that comes in at an angle if we have alpha between -1 and 0. As it turns out, loudspeakers have a major fraction of their behavior along this sort of diagonal, and electrodes have a major fraction of their behavior along this sort of capacitor-like direction. And so these turn out to be this formula turns out to be very useful for modeling loudspeakers and electrodes, the two devices that we actually end up modeling in this course. They're not standard, though, because we don't have a differential equation that has this formula as a solution. For special cases, alpha equals 0, -1, and 1, we do have differential equations. And having differential equations for the behavior of a device is very useful for both analytic solutions and for numerical modeling. So the formula here is non-standard because it's not quite as useful as the standard formulas for mathematical manipulation, though it is more realistic in modeling a number of devices. And we will see more about this when we actually try modeling loudspeakers.